So far, we've been looking at different expressions for electric potential energy. And now I would like to transition over to a related concept called the electric potential without the word energy after it. This is an unfortunate, they are different physical quantities, but very unfortunately, they have very similar sounding names in English. I'll get more into that in a bit. But first, I would just like to start with a little thought experiment. In fact, I'm actually going to ask you to, once I set this up, to pause the video and do the calculations here. Let's say I place a charge Q1 here, and it has 1 microcoulomb of charge. And now, let's say 5 centimeters away, I place a charge Q2 right here. And what I would like you to get for me is what the value of the electric potential energy for this system is for the choices of charge Q2 of plus 1 microcoulomb, minus 5 microcoulombs, plus 20 microcoulombs, and minus 8 microcoulombs. And I would also like you to just pay attention to how you're doing the calculations, see if there's anything you're doing that might be speeding them up. So go ahead, pause the video, do the calculations, and then we'll get back to this. All right, so this is a plug and chug here. You should have been saying, okay, yeah, the potential energy is K Q1 Q2 over R. Now, what I'm hoping that you might have realized, and if you didn't, it's okay. I'm hoping you might have realized that these numbers here never change. And so if you're trying to speed up the process, it might have occurred to you to pre-compute those values. So we can go ahead and figure out what that would have been equal to. This would have been 9 times 10 to the 9 Newton meters squared per coulomb squared. Our Q1 is 1 microcoulomb, so it's 1 times 10 to the negative 6 coulombs. And then we would have divided that all by 0.05 meters. And we would have figured out that that part of it was 180,000. And let's think about the units for a second here. Meters cancel here. 1 power of coulomb cancels here. Now I know that when I times by this other charge, I'll cancel this other coulomb and I'll be left with newtons times meters, but this is an energy. So it'd be make more sense to express Newton times meters as joules, and you would have had joules per coulomb there. So with that bit of pre-computation out of the way, you could then go ahead and say, all right, for the first case, I can take 180,000 joules per coulomb, and I can times that by 1 microcoulomb, which is 1 times 10 to the negative 6 coulombs, to get me 0.18 joules. And oops, there we go. And then similarly, you could have done the other charges by just plain multiplying this exact same number by whatever charge you cared about. So for the next one, for instance, you would have gone ahead and times it by negative 5 times 10 to the minus 6 coulombs, and you would have gotten negative 0.9 joules. And then you could have, and then you could have, there we go. And then you could have times it by the next charge in the sequence, which was 20 joules, 20 microcoulombs. So that would have given you 3 plus 3.6 joules. And then finally, you could do the minus 8. So that would have been... Eck. There we go. So that would have been times -8 times 10 to the minus 6 coulombs. So that would have been, let's see, 64, 5.4. Would have been whatever this was. Sorry, I don't have my calculator in front of me. Okay, this is going to drive me nuts, so I'll just do it. There we go. 1.44. Negative 1.44 joules. So this would have saved a whole lot of effort because you wouldn't have had to keep multiplying and dividing all these numbers together. You just do it once and then you remember it. Although it's more than just the cute computational trick that I'm showing you, what we've basically done is we've almost invented a quantity called the electric potential, also known as the voltage. So let's go ahead and do a more formal definition of the electric potential. And so you'll notice I'm being very careful to talk about the electric potential as opposed to the electric potential energy. These are related concepts, but they are different physical concepts. We will define the electric potential, which we usually use the symbol capital V for, to be the potential energy of a system that involves a test charge with the test charge divided back out. And then later, when you have a real charge at some location, you can take the electric potential at that point, times it by that charge, to get the potential energy of the system, like we just did in our little thought experiment. So, for instance, if we have a uniform electric field, we saw that the potential energy was QEX. And so we can go ahead and divide both sides through by the voltage, by the charge, to get just E times X. And similarly for a point charge, this is the exercise we just did. Effectively, when you divide out the test charge, we get that the voltage at any point due to a source charge would be 1 over 4 pi epsilon naught. Remember, that's our K. Q, that's our source charge. R, that's the distance to the location space. So this is, again, a value associated with the location in space. And then it's just saying, if I choose to put a charge at that location space, the potential energy of the electric potential energy of the whole universe now is that number times the charge I put at that location space. So the units of this are the volt. And the usual symbol we use for volt is a capital V. So again, be careful here. This V is a unit. This V here is the symbol, which is also very unfortunate. And it is 1 joule per coulomb. So what's up with the name? Potential energy, that's the quantity with the U, The word potential there in English is coming mostly from the idea that you have the potential to do work. This potential here from electric potential is actually a different meaning in the word potential. That's some math jargon. And so although they are the same word, they're being used in very different ways. This problem does not exist in other languages, but this is in English, and this is a common thing. And it gets confusing enough that what a lot of physicists have started taking to doing is, instead of calling, they will always say the electric potential energy if they mean the electric potential, and if they mean the energy. But if they just mean the electric potential without the word energy after it, a lot of people now are starting to call it the voltage. And I've started reluctantly doing that myself. After all, you don't call force Newtonage, right? That seems kind of silly. But here, just the terms are just so confusing that referring to the quantity by its typical unit, although that's leaves a little bit of a bad taste in your mouth, maybe that's a better choice than having to be very careful and say, did they say electric potential or electric potential energy? I'll probably say both electric potential because I was trained a bit on the old school side, and voltage. I'll probably be going back and forth between those terms. And again, here, just to note real quick, this would be the voltage out at infinity would be set equal to 0 to stay consistent with what we did for electric potential energy. So now we'll loop back for just a second and talk about units of electric field. So now that we've got the volt, it's time to tell you how physicists usually write units of electric field. So far we've been writing it as a Newton per Coulomb, but physicists usually write it actually as volt per meter. And that will make more sense as we explore the interrelationships between electric field and voltage. But you should go ahead and do the unit conversion for yourself to convince yourself that this actually works out to be newtons per coulomb. So go ahead, pause the video right now, give that a try, and see where we get. Okay. So we said a volt is a joule per coulomb. So we have a joule per coulomb per meter. A joule is a Newton times a meter per coulomb per meter. So we're left with this being indeed a Newton per coulomb as advertised. So both units get used, but in working use, physicists usually say volt per meter. All right, so how can we interpret this quantity? Well, one thing we can look at is, let's say we're just in some region here, and we're just saying as we go this way, the voltage increases in this direction. All right, so now let's think about what that would mean for, say, a positive charge that I have here. Let's say it's initially moving with some velocity v, like so. As we move from this location to this location here, the change in the voltage would be would be positive, because my final is greater than the initial. And since we remember that the potential energy is the charge times the voltage at the location, we can then say, oh, that means that the potential energy at that location must also have increased. Well, where'd that energy come from? It had to come from kinetic. So it must be that it's going slower now. All right. And again, we could say, well, what if our charge was moving to the left initially? Then what would happen? When we get over here, we're now in a direction where things are decreasing, so delta V would be negative. And so this would mean that the potential energy of the charge also had a negative change. So this would mean the kinetic energy would have had to go up, and so we get that the charge is going faster now. And let's just go to make sure that we've dotted all the I's and crossed all the T's. Let's go and revisit this exact same scenario for negative charges. So here, if I go from here, and I was initially going this fast, and now I end up here, it's still the case that the voltage increased. But since the potential energy is the charge times the voltage, this would mean the potential energy decreased. So that means the kinetic energy had to have increased, and so our negative charge would have picked up speed. Similarly, if we went in the other direction, went over to here, the change in the voltage would be negative, but this would mean that the change in the potential energy would be positive. And that energy had to come from somewhere, so it would have come from the kinetic energy. And so now we're moving slower. Alrighty, so in the next video we will take a brief interlude into a unit called the electron volt and how it's handy for certain kinds of physics calculations. See you there.